Hello everyone, this is Professor Roman. Welcome to the 30th video in my video lecture series, An Introduction to Discrete Mathematics. In this video, we're going to start chapter 6 of the accompanying book, Recurrence Relations. Recurrence relations are extremely important, not just in mathematics, but they have a great deal of applications to other areas. We'll talk about that just briefly. In the year 1202, a mathematician named Leonardo Fibonacci, whom you may have heard of, posed the following counting problem, which he phrased in terms of the breeding of rabbits. A breeder of rabbits keeps the rabbits in male-female pairs in a cage by themselves. Assume that a rabbit pair can produce offspring only on the last day of a given month, and that a rabbit pair does not reproduce at the end of their first month of life because they're too young, but do reproduce a new pair of offspring at the end of each subsequent month. Once they're 2 months old, they begin to reproduce. Then the newborn pairs move to an empty cage. Now, if the breeder starts with a single pair of newborn rabbits, and if we assume no rabbits die, how many rabbits will the breeder have after n months? That is the question. Well, to solve this problem, let's denote the number of pairs of rabbits at the end of the nth month by S sub n. So S sub 1 equals 1. And I'm going to call this pair of rabbits Fred and Ethel. If you're old enough, you may recognize those names. At the end of 2 months, Fred and Ethel will produce a pair of offspring, which I will call George and Gracie. And so S2 equals 2. At the end of the 3rd month, Fred and Ethel will produce another pair of offspring, but George and Gracie are too young to reproduce. So S3 is equal to 3. In general, just before the last day of the nth month, so just before the new rabbits are born in the nth month, there are Sn-1 pairs of rabbits. But these pairs can be split into 2 categories. There are the pairs that are now at least 2 months old, and so they can reproduce. That number is Sn-2. And then the remaining pairs, Sn-1 minus Sn-2 pairs, they're only 1 month old, so they're not going to reproduce. So on the last day of the month, the Sn-2 older pairs produce an additional Sn-2 new pairs, and therefore Sn is Sn-1, that's the existing pairs, and then we have to add the new pairs, Sn-2. And this is true for n bigger than or equal to 3. However, if we just set S0 equal to 1, then this will also hold for n equals 2. And this equation simply says that once you get to the 3rd term, any given term is the sum of the 2 previous terms. Very simple. This equation, together with the first 2 terms, S0 equals 1 and S1 equals 1, are sufficient to determine any terms in the sequence. So we start with 1 and 1. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. and so on. This equation is an example of a recurrence equation or recurrence relation. Finding a general formula for the rabbit problem, Sn, that's another matter. So there are two steps in dealing with problems that are amenable to recurrence relations. One is finding the correct recurrence relation, and the second is, if appropriate, finding a general formula for the nth term. And you'll see what I mean by is appropriate as we continue. But just to give you a hint, let me show you something. Here is the formula for the nth term in this Fibonacci recurrence relation. It's pretty ugly. It's even surprising that all of this is an integer. But we'll get to this later on. Here's the formal definition of a recurrence relation. Let Sm, Sm plus 1, and so on be a sequence of numbers starting with starting index m. Usually m is 0 or 1, but it can be anything, doesn't matter. A recurrence relation for this sequence is an equation that expresses the general term S sub n of the sequence in terms of previous terms in the sequence. A solution to a recurrence relation is a formula of the form Sn equals some function of n. This is a formula for the general term Sn that does not involve any terms of the sequence. F of n does not involve any terms of the sequence. The values of the first few terms that are required, no more, no less, in order to compute any member, in a sense all members of the sequence, using the recurrence relation, are called the initial conditions of the recurrence relation. So in the example we've been doing, we need two initial conditions, and then we can compute any term we want. Recurrence relations occur quite frequently, as I said before, in many branches of math and the sciences. For example, they occur in physics, computer science, statistics, genetics, botany, economics, psychology, sociology. They're ubiquitous in applications. And there are entire books written on the subject of recurrence relations, which are also known as difference equations. So in this section, we're going to look at some examples of counting problems that lead naturally to recurrence relations. I'm also going to discuss the most rudimentary, the simplest method for solving such equations to get a solution, a direct formula for the general term. In the next two sections, we'll look at some more sophisticated approaches to solving recurrence relations. The sequence S sub n that we've been looking at here, the rabbit sequence, is, I guess you've guessed by now, called the Fibonacci sequence. And the numbers are called Fibonacci numbers. And we're going to encounter them again. They're remarkable numbers. As a matter of fact, the Fibonacci numbers occur in some remarkable places in nature. For example, some plants, on some plants, the thorns and the leaves grow in a spiral pattern, and the number of thorns or leaves per revolution about the stalk is a ratio of two Fibonacci numbers. So for instance, the apple and the oak tree have 5 growths for every 2 turns around the stalk. And if we go back here, 5 for every 2. What else? The pear tree has 8 growths for every 3 turns. The willow tree has 13 growths for every 5 turns. I have no idea why this is, but if you're interested in exploring this further, I found a good reference, a book by Peter Stevens called Patterns in Nature. It's probably on Amazon. Okay, so let's turn to some examples of counting problems that lead to recurrence relations in a more or less natural way. Well, I'm not going to attempt to do the solutions when we look at these examples. That will come later. I may do some, but one of the simplest recurrence relations arises from the problem of determining the number Sn of subsets of a set of size n. We've done that in 2 different ways already. In the first case, we just guessed the formula and proved it by induction. In the second case, we used the fundamental counting principle or multiplication rule. Now we're going to do it by recurrence. So let's let S be the set 1 through n. The subsets of S can be divided into 2 groups, those that contain n and those that don't. Well, there are Sn minus 1 subsets of S that don't contain n. But there are as many subsets of S that do contain n as subsets that don't contain n. You can go back and forth in a one-to-one fashion between these 2 families of subsets just by tossing in n or removing it if you're going in the other direction. So Sn is Sn minus 1 plus Sn minus 1, or in other words, 2 times Sn minus 1. Okay. That is the recurrence relation starting with the initial value S0 equals 1, and that's the sequence for Sn. This example is a lot more interesting. I spoke a while ago about this Towers of Hanoi game. This problem of counting the minimum number of moves required to complete the game also leads naturally to a recurrence relation. I'm going to spell that right. So here's the initial configuration. And the game has 8 rings, and you have to move them from peg 1 to peg 3 under the conditions that only 1 ring can be moved at a time, and you can't put a larger ring on top of a smaller ring. And as I say, the problem is to determine the minimum number of moves required to complete the task. Now, our solution is going to work equally well for any number of rings. So let's assume there are n rings on 1 peg at the start, and let Sn be the minimum number of steps required to move all those n rings to a different peg. There's a certain symmetry as far as the pegs are concerned. It's not as apparent when they're lined up in a linear fashion, but we can see that symmetry a lot better if I put the pegs at the vertices of an equilateral triangle. So that's what I'm going to do. It doesn't affect the game at all. Okay. The initial value S1 is 1. If you only have 1 ring, no big deal, you just move it. Now I've identified the 3 pegs here by color, and I'm I hope you can see that. This is a black peg, this is a green peg, and this is a red peg. You can also use the position to identify them. So we're starting off with all end pegs on this upper left, all end rings on the upper left peg, the black peg. And it doesn't really matter. We could have started the initial conditions, the configuration with all these rings on any one of the three pegs. They're all equivalent. We have to move them to a different peg. Now, this is the key here. In order to complete the game, there must come a step, let's say the kth step, when we first place the largest ring onto the final peg. And that's going to be, in the picture, it's going to be the red peg. If we're going to get all the rings from the black peg to the red peg, at some point we're going to have to move the largest ring. And at that point, the red peg will be empty, and we'll put the largest ring on it. Okay. So step k-1, after that's completed, we have this configuration. All of the other rings have to be on, let's call it the holding peg, it's the green peg, in order to clear the largest ring so we can move it over to the red peg at step K. Now we can divide the entire procedure into three parts. Steps 1 through k-1, which leads us to this configuration here. Then step K, which puts us over here. And then the rest of the steps, k+1 through Sn, if it's an optimal procedure, right? Minimum number of steps. Moreover, if we can determine the minimum number of steps required to complete each of these three parts, their sum will be the fewest number of steps required to complete the entire game. You see, the point is it doesn't help. You might think, well, we'll sacrifice a couple of, put in a couple extra steps in part 1, and that'll maybe allow us to save a lot more steps in part 3. It doesn't work that way, because you get to this configuration, no matter how you do it, you still have to go from here to this step and then to the final step. So they're independent procedures. Okay. Well, obviously part 2 requires one step. Part 1 requires Sn-1 step. K-1, Sk-1 steps. It's this last part where it becomes a little tricky. Once we've placed the largest ring on the red peg, it seems intuitively clear that we should never move that ring again. But we need a little bit more convincing argument than intuitively clear. For that, note that the largest ring can only be moved when all the other rings lie on the same peg, and not on the peg containing the largest ring. Okay. So there's a lot of restriction on moving the largest ring. And these two configurations are essentially the same as far as how many moves it's going to take to finish the game. That's the symmetry I was talking about in the pegs that seems pretty clear from these pictures, but maybe not as much when the pegs are in line. Maybe so, I don't know. Just seemed like a good idea at the time to put them in a triangular configuration. So we can pretty much ignore this one and assume that when the largest ring is moved, all the other rings are in this bottom left peg. Okay. Well, now looking at this, would it make any sense to move the largest ring again? It can only be done when we have this configuration. And if we move it up to the black peg, we've just backed up a step. We've done a move and then we've undone it. So that's a waste of steps. Okay. And the same kind of argument could be made if this was the configuration. So from this point of view, it seems pretty clear that you don't want to move that largest ring again. So the most efficient way to complete the game is to first use the minimum number of steps required, Sn-1 steps, to move all but the largest ring off of the initial black peg. And we can say to the green peg. Then move the largest ring to the black peg. And then finally, since we're never moving the largest ring again, we can pretend it's not even there. It's going to take another Sn-1 steps to move the remaining rings from the green peg to the black peg. So Sn is Sn-1 plus 1 plus Sn-1, or in other words, it's this. This is the Towers of Hanoi recurrence relation with initial condition S1 equals 1. Now you can compute any Sn you want. Okay. S2 is going to be 2 times 1 plus 1, or 3, and so on. Also, this discussion, this description, kind of tells you how to complete the game, not just what the minimum number of moves is that's required, but how you would actually do that. And there's still some thinking to be done here, so I'm going to leave that for you if you're interested. Let's move on to another example. A set of straight lines in the plane is said to be in general position if no two of the lines are parallel and no three of the lines go through the same point. How many regions do n lines in general position divide the plane? Well, the way to handle problems like this at the start is to draw a few pictures, think about simple cases until it becomes clear what the question is even. So a single line divides the plane into two regions. Okay. Two lines in general position means two non-parallel lines. They're going to give you 4 regions. 3 lines in general position will look like these 3 lines here. No 2 are parallel, no 3 go through the same point. And if you count and number these, you get 7 regions. Some regions are unbounded. There's 1 bounded region. So if we let Pn be the number of regions created by n lines in general position, P1 is 2, P2 is 4, P3 is 7. That should hopefully be enough to cover the initial conditions. We may, in fact, not even need all of these. or that is to say we may not need P3. Let's see if we can find a recurrence relation for this sequence Pn. So consider a set of n minus 1 lines in general position in the plane. And these lines divide the plane into Pn minus 1 regions. Now imagine including one more line in general position. What does it do to the regions that were existing before you added the line? So I've drawn that new line in bold. And there are 4 other lines that were there beforehand. Okay, so we're up to n equals 5. Since no 3 lines go through the same point, the new line will intersect each of the n minus 1 lines at a different location. Okay. In other words, the black line here can't intersect at a point of intersection of earlier lines, of existing lines, because then all 3 would go through the same point. The first intersecting point, which should be right here, splits an unbounded region into 2. So it was region 1 up here, got split into 1A and 1B by this line. It's the first time the new line intersects one of the existing lines. The second intersection point splits another region, maybe bounded, maybe not, but in this picture it's bound. It's not bounded, into 2 regions, 2A and 2B. And this continues. Every time the new line hits an old line, it splits the region bounded by the old line into 2 parts. So a total number of n regions are split into 2 parts because this line makes n intersections with, makes n minus 1 intersections with the old lines, but then it exits somewhere and gives you another split. So Pn is Pn minus 1 plus n. There are n new regions. N minus 1 because of the initial intersections, and then the exit gives us 1 more. Okay. Another area in which recurrence relations occur naturally is in trying to count words that have some restriction placed on their pattern of letters. So let's look at a couple of examples. Suppose we want to count the number of binary words that do not contain 2 or more consecutive zeros. So in other words, they do not have this simple pattern, 0, 0. Well, this is, again, a natural place for recurrence relations. So let Sn be the number of such words. We can classify these words according to their first bit, which is, of course, either a 0 or a 1. If the first bit is a 1, then the word has this form, W equals 1U. U is a word of length n minus 1, and it cannot contain the forbidden bit pattern, 0, 0. So there are Sn minus 1 of those words. If the first bit is a 0, then the second bit has to be a 1, and so the word looks like this, where U is a word of length n minus 2, that doesn't have the bit pattern 0, 0. So there are Sn minus 2 of those. Well, therefore Sn is the sum of Sn minus 1 and Sn minus 2. And this is good for n bigger than or equal to 2, which is the Fibonacci recurrence relation. But in this case, the two required initial conditions are different than they are in the rabbit case, in the Fibonacci sequence case. S naught is 1, the empty word qualifies, and S1 is 2. You can have 0, 1, 1, 0. I'm sorry, S1 is 2 because you could have a 0 or a 1. Okay. So this is not the Fibonacci sequence, only because the initial conditions are different. Let's do another example. Find a recurrence relation for the number Sn of binary words W of length n that do not contain this bit pattern 0, 0, 1. Well, these words fall into one of three groups. The word W may start with a 1, so it looks like this. U has length n minus 1 and no forbidden substring 0, 0, 1. So there are Sn minus 1 of those words, same as the last example. W may start with 0, 1, in which case it looks like this. U has length n minus 2, and again, no forbidden pattern. So there are Sn minus 2 of those. And finally, W may start with 0, 0, in which case the next bit has to be a 0, and then the bit after that has to be a 0. In other words, it's going to have to be the word with all zeros, and there's one of those. So this is what the recurrence relation looks like. And these are the initial conditions. I hope you can see that this type of problem is is perfect for recurrence relations. So now that we've looked at some examples, let's discuss how we might solve recurrence relations. At least the simplest way, the simplest method available to us, which is called iteration. And the idea is simply that you use the recurrence relation over and over again for different indices in the hopes of seeing a pattern. And you can guess at the pattern, guess a formula, and then you can verify it against the recurrence relation and the initial conditions. So let's try some of that. As I mentioned before, we'll do some more sophisticated methods in later sections. So let's look at this recurrence relation, which we saw earlier for the number of subsets of a set of size n. Initial condition S naught equals 1. This one is so simple you can probably guess right away. Well, you know what it is because we've done this sort of thing before in different ways. But let's take it one step at a time just to demonstrate the method. There's kind of two approaches here. You can work from the bottom up or from the top down, so to speak. If we go upward, we start with the first element of the sequence, S naught. Twice that is S1. And then if we, then to compute S2, it's twice S1, which is twice 2S naught. So that's 2 squared S naught. And rather than writing 4, I write 2 squared in the hopes to see a pattern. So that's called the first iteration of the recurrence relation. The second iteration gives us S3 as twice S2, which is 2 cubed S naught. And by now, the pattern looks very clear. Sn should be 2 to the n S naught. And all you have to do is plug it back into this formula to see that that's the case. Twice this would be Sn plus 1. Okay. You could also verify it by induction if you want to be more formal. The downward approach is quite similar, maybe not as obvious, but you start with Sn equals 2Sn minus 1, replace Sn minus 1 by Sn twice Sn minus 2, and then again replace Sn minus 2 by twice Sn minus 3, and you begin to see this pattern, and then you can set k equals k equals n, and you'll get the same thing we had before. Sometimes one direction's easier than the other. So another example, this was the towers of Hanoi recurrence relation. Starting from the bottom, S2 is 2S1 plus 1. S3, the first iteration, is then twice the quantity 2S1 plus 1 plus 1, and expanding that looks like that. And again, rather than writing 4, I write 2 squared. One more iteration, and we're looking at this. And also, rather than writing 3, 2 plus 1, because we're looking for a pattern. And I think we see one here fairly clearly. When this index is 4, we have sums of powers of 2 starting with the third power, and we stick S1 right here. Multiply the highest power of 2 by S1. So for Sn, we have these powers of 2 starting with 2 to the n minus 1, and here's the S1. And I just put the parentheses for readability. Well, we learned a long time ago how to evaluate the powers of a real number, the sums of powers of a real number. So it comes out to be this, and that reduces the recurrence relation to this. Okay. And you can factor out the 2 to the n minus 1 here if you wanted. But the initial conditions, S naught, S1 equals 1, replaces this S1 here with 1, so we get twice 2 to the n minus 1, or in other words 2 to the n, but we have minus 1 here. So this we can check by induction. For the actual towers of Hanoi problem, there are 8 rings, and so there are 255 moves required to complete the towers of Hanoi puzzle. Another example, this was the n lines in general position recurrence relation. Initial condition P1 equals 2. 2 regions when you have one line. So again, iteration, first step, first iteration, replace P2 by P1 plus 2, replace P3. P4 is then P3 plus 4, replace P3 by P1 plus 2 plus 3, right? This goes in for this. And we already see a pattern. It looks like Pn is going to be P1 plus 2 plus 3 plus 4 up to n, because this 4 and this 4 is 4. Okay, so that's what we have here. And what I did, just to make this a little easier to cope with, I wanted this sum not to go from 2 to n, but from 1 to n, so I subtracted 1. Because this sum is n plus 1 choose 2, and so Pn is P1 minus 1 plus n plus 1 choose 2. Using the initial condition P1 equals 2, we get this nice looking formula. And again, we have to check this. We have to verify. 100 lines in general position then will create 5,051 distinct regions. Okay. And I think you have to admit, even if you're not all that keen on this, that this is pretty impressive. We've found a very simple technique, a mathematical technique, for computing the number of regions that the plane is divided into if you have any number of lines in general position. 100 lines, 5,051 regions. I think that's pretty impressive. Okay, shows the power of, well, mathematics in general, but in particular, counting techniques. Okay, that concludes the section and this video. In the next video, we'll talk about second-order linear homogeneous recurrence relations with constant coefficients. It's a mouthful, but it's not as bad as it looks. They just look like this. Sn equals A Sn minus 1 plus B Sn minus 2. Thank you for watching, and I hope to see you in the next video.